What if the most powerful telescope humanity has ever built is showing us a universe that should not exist in the way we expected? For centuries, we looked into the night sky and believed that the farther we could see, the more complete our picture of the cosmos would become. Then the James Webb Space Telescope changed the rules. Launched into space in December 2021, Webb was designed to look deeper into the universe than previous observatories, using infrared light to reveal objects hidden by cosmic dust and to detect some of the earliest galaxies ever observed. And what it has seen is extraordinary. Galaxies appearing surprisingly bright and surprisingly developed at a time when the universe was still extremely young. Stars being born inside enormous clouds of gas and dust. Ancient galaxies colliding and transforming one another. Planets orbiting distant stars. Atmospheres that may contain the chemical ingredients needed to understand how worlds evolve. And structures so distant that their light began its journey toward Earth billions of years before our planet even existed. But there is something about these images that is easy to misunderstand. When you look at a spectacular James Webb image, you are not simply looking at a distant place. You are looking into the past. Sometimes, into a past so ancient that the light reaching the telescope began its journey before the Sun, Earth, and even the Milky Way as we know it had fully formed. Every photon carries a piece of history. And Webb has become extraordinarily good at collecting those ancient pieces of information. But the deeper it looks, the stranger the story becomes. Because some of the earliest galaxies observed by Webb appear more massive, more luminous, or more structured than astronomers initially expected from simple models of how galaxies should have evolved. Does that mean our understanding of the early universe is wrong? Not necessarily. Science rarely changes because a single observation instantly destroys an entire theory. Instead, surprising observations force scientists to examine their assumptions. Perhaps galaxies formed more efficiently than expected. Perhaps the earliest stars were different from the stars we see today. Perhaps some of these objects are being interpreted incorrectly. Or perhaps the physics governing the growth of the first galaxies contain something we have not yet fully understood. And that is where the real mystery begins. Because James Webb is not simply taking beautiful pictures. It is allowing us to test ideas about the origin and evolution of the universe itself. It can observe galaxies whose light has traveled for more than 13 billion years. It can examine stellar nurseries hidden behind clouds of dust. It can study the atmospheres of distant exoplanets by analyzing the faint fingerprints that molecules leave in starlight. And it can reveal details of cosmic objects that were previously little more than points of light. The deeper Webb looks, the further back we travel. And eventually, we approach an extraordinary boundary. A time when the first galaxies were beginning to emerge. A time when the universe was still young. A time when the cosmic structures we recognize today were only beginning to take shape. So what exactly has James Webb seen? Which discoveries have genuinely challenged astronomers? Which apparent mysteries have already been explained? And which observations are still forcing scientists to rethink what they believed about the early cosmos? In this journey, we are going to travel through some of the most remarkable observations made by the James Webb Space Telescope. But we will also separate fact from speculation. Because the universe does not need exaggerated claims to be astonishing. The real discoveries are already incredible enough. And before we begin, if you enjoy exploring the deepest mysteries of space, discovering how the universe really works, and traveling through the cosmos from the comfort of your screen, subscribe to the channel and join us for this journey. Because what James Webb has seen is not simply a collection of distant images. It is a record of cosmic history. And the farther we look, the closer we get to the beginning. To understand why the James Webb Space Telescope has been so transformative, we first need to understand what came before it. For decades, astronomers relied on telescopes that revealed different portions of the electromagnetic spectrum. Among the most important was the Hubble Space Telescope, launched in 1990. Hubble changed our view of the cosmos. It showed us galaxies in extraordinary detail, revealed stars being born and dying, and allowed astronomers to observe some of the most distant objects ever detected. But Hubble was primarily designed to observe visible and ultraviolet light. And that created a problem. The early universe is not necessarily easiest to understand using visible light. As the universe expands, the wavelengths of light traveling through space are stretched. This phenomenon is called cosmological redshift. Light that began as ultraviolet or visible radiation can arrive at Earth after billions of years with its wavelength stretched into the infrared part of the spectrum. So if astronomers wanted to investigate the earliest galaxies, they needed an observatory capable of seeing infrared light with extraordinary sensitivity. That was one of the central reasons James Webb was built. But Webb was not simply a larger version of Hubble. Its design required an entirely different approach. The telescope has a primary mirror approximately 6.5 meters across, composed of 18 hexagonal segments. That enormous mirror allows Webb to collect far more infrared light than Hubble. But there was another challenge. Infrared observations are extremely sensitive to heat. Anything warm emits infrared radiation. If the telescope itself became too warm, its own thermal emission could overwhelm the faint signals arriving from distant galaxies. So Webb needed to operate at extremely low temperatures. The solution was one of the most remarkable engineering achievements in modern space science. A giant 5-layer sunshield, roughly the size of a tennis court, protects the telescope from the heat and light of the Sun, Earth, and Moon. Webb was launched on December 25, 2021, aboard an Ariane 5 rocket from French Guiana. But launching the telescope was only the beginning. Once in space, Webb had to perform a sequence of incredibly precise deployments. The solar panels had to unfold. The communication systems had to activate. The enormous sunshield had to deploy. The primary mirror had to open. And its 18 segments had to be aligned with extraordinary precision. The telescope eventually traveled to a region known as the Second Sun-Earth Lagrange Point, or L2, approximately 1.5 million kilometers from Earth. There, Webb could maintain a stable observing geometry while remaining protected from the strongest sources of heat. It was an extraordinary mission. And then came the moment astronomers around the world had been waiting for. The first full-color images were released in July 2022. The public saw enormous clouds of gas, distant galaxies, dying stars, and gravitational structures rendered with a level of detail that had never been available before. One of the most famous images was the SMACS 0723 deep field. At first glance, it looked like a field of stars. But many of the tiny points scattered across the image were not stars at all. They were distant galaxies. Thousands of them appeared within a tiny patch of sky. And that image contained another remarkable phenomenon. Some galaxies appeared distorted, stretched, or magnified. This was caused by gravitational lensing. According to Einstein's general theory of relativity, massive objects curve space-time. When light from a distant galaxy passes through the gravitational field of a massive galaxy cluster, its path can be bent. The cluster effectively acts like a cosmic magnifying glass. This allows Webb to observe some objects that would otherwise be too faint or distant to detect. It also means that certain images produced by Webb are not straightforward photographs. They are the result of light traveling through a universe whose geometry has been altered by gravity. And this is one reason Webb can look so far back in time. It combines an enormous infrared collecting mirror with instruments capable of analyzing faint light in extraordinary detail. One of those instruments is NIRCam, the near-infrared camera. It captures near-infrared observations and is central to many of Webb's deep-field studies. Another is NIRSpec, the near-infrared spectrograph. Instead of simply recording how bright an object appears, spectroscopy allows astronomers to separate its light into different wavelengths. Those patterns can reveal information about chemical elements, physical conditions, motion, and distance. This distinction is critical. A picture can tell us that something exists. A spectrum can begin to tell us what it is made of. Webb also carries MIRI, the mid-infrared instrument, which extends observations into longer infrared wavelengths. And it has NIRIS, the near-infrared imager and slitless spectrograph, along with the fine guidance sensor that helps the telescope point with extraordinary accuracy. Together, these instruments transformed Webb into something much more powerful than a camera. It is an observatory designed to investigate the history and physics of the cosmos. And one of its most ambitious goals was to look back toward the earliest generations of galaxies. This is where the story became particularly interesting. Before Webb launched, astronomers already had evidence of very distant galaxies from previous observatories. But the new telescope could detect fainter infrared light and measure the spectra of extremely distant objects. Very quickly, Webb began identifying galaxies at enormous cosmological distances. Some appeared to have existed when the universe was only a few 100 million years old. That was already extraordinary. But then some observations appeared to challenge expectations about how quickly galaxies could grow. Astronomers found candidates that looked unexpectedly bright. Some appeared surprisingly massive. And a few seemed to contain more complex stellar populations than certain early universe models had predicted. Headlines began appearing around the world suggesting that James Webb had broken cosmology. But the real scientific story was more complicated. Some early distance estimates were later revised. Some objects turned out to have properties that could be explained by processes that had not been fully accounted for. And the interpretation of distant galaxies depends heavily on spectroscopy, stellar populations, dust, star formation rates, and the assumptions built into the models. In other words, the telescope did not simply reveal that everything scientists believed was wrong. It revealed that the early universe was more complicated than many simplified expectations suggested. And this is precisely how science is supposed to work. A prediction is made. A new observation arrives. The observation is tested. The data are analyzed. The models are revised if necessary. And sometimes, the result reveals something genuinely unexpected. Webb's discoveries have also extended far beyond ancient galaxies. It has observed enormous stellar nurseries such as the pillars of creation, revealing structures hidden within clouds of dust. It has examined regions where new stars are forming. It has observed distant planets passing in front of their host stars. And during those transits, a tiny fraction of starlight can pass through the planet's atmosphere before reaching the telescope. That light can contain molecular fingerprints, water vapor, carbon dioxide, methane, other molecules. The detection and interpretation of these signals is extraordinarily difficult. But it gives astronomers a completely new way to investigate worlds beyond the solar system. For the first time, humanity is not merely discovering distant planets. We are beginning to study their atmospheres. And that changes the question. Instead of asking only, is there a planet there? We can begin asking, what is that planet's atmosphere made of? How hot is it? How does its chemistry behave? And under the right circumstances, could its atmosphere contain clues about the conditions on its surface? These are enormous questions. But Webb was designed to investigate them. And as the telescope continued observing, one pattern became increasingly clear. The universe was not simply revealing more objects. It was revealing more complexity. The first galaxies were not necessarily simple collections of primitive stars. Stellar nurseries were far more dynamic than earlier images had suggested. Distant planetary atmospheres could be chemically diverse. And structures that appeared simple from Earth often contained layers of physical processes hidden inside them. But perhaps the most important discovery was still waiting in the deepest observations. Because when Webb looked toward the earliest galaxies, astronomers began confronting a difficult question. How did the universe build such complex structures so quickly? To answer that, we need to understand what the scientific models actually predicted about the first galaxies, the first stars, and the growth of cosmic structure. And that is where the extraordinary images from James Webb become much more than beautiful pictures. They become tests of our understanding of how the universe came into existence. To understand why the James Webb Space Telescope has made such a profound impact, we need to understand what its observations are actually telling us. The key is light. Light is not simply what allows us to see distant objects. It is the primary source of information we have about the universe. When light leaves a distant galaxy, it carries information about the stars that produced it, the gas surrounding them, the motion of the galaxy, and the chemical elements present within it. But that light also carries a record of the universe's expansion. As space expands, the wavelengths of traveling light are stretched. The farther the light has traveled through an expanding universe, the more its wavelength can be shifted toward the infrared. Astronomers describe this as cosmological redshift, represented by the letter Z. And redshift is one of the reasons James Webb can look so far into the past. Imagine a galaxy that emitted ultraviolet light billions of years ago. As that light traveled across the expanding universe, its wavelength became progressively longer. By the time the photons reached the vicinity of Earth, much of that original radiation could have shifted into infrared wavelengths. A telescope designed primarily for visible light might struggle to detect it. Webb was specifically engineered to capture it. This gives astronomers a remarkable ability. By measuring the redshift of a distant galaxy, they can estimate how much the universe expanded while its light was traveling toward us. The larger the redshift, generally speaking, the farther back in cosmic history we are looking. But redshift alone is not enough. Astronomers also need to understand what they are seeing. And this brings us to one of the most important scientific questions Webb is helping investigate. How did the first galaxies form? The early universe was not filled with mature galaxies like the Milky Way. After the Big Bang, the cosmos was initially extremely hot and dense. As it expanded and cooled, elementary particles formed increasingly complex structures. Eventually, protons and neutrons combined into atomic nuclei. Later, electrons combined with those nuclei to form neutral atoms. The universe became transparent to light. But there were not yet galaxies shining across the darkness. There was a period often called the Cosmic Dark Ages. The universe contained matter, but no abundant stars had yet transformed it into a luminous cosmic landscape. Gravity gradually amplified tiny variations in density. Some regions contained slightly more matter than others. Those regions had stronger gravitational attraction. They gathered additional matter. Over time, enormous structures emerged. Dark matter played a crucial role in this process. Although we cannot see dark matter directly, its gravitational influence appears to provide the underlying framework around which galaxies form. Gas fell into these growing gravitational wells. It compressed. It heated. And eventually, the first stars ignited. Those first stars were fundamentally important. They transformed the chemistry of the universe. The early cosmos was composed primarily of hydrogen and helium, with only tiny amounts of other light elements. The heavier elements familiar to us today, carbon, oxygen, silicon, iron, and many others, were produced through stellar processes and released into space when stars evolved and died. Later generations of stars formed from this increasingly enriched material. Galaxies became chemically more complex. Planets eventually became possible. And much later, life emerged on at least one world. This means that when Webb observes an ancient galaxy, it is not merely observing a distant collection of stars. It is observing a stage in the construction of the universe we live in today. But there is a problem. Galaxies need time to grow. According to the standard picture, small structures formed first. They merged. They accumulated gas. Stars formed. The galaxies became larger and more complex. This process should take time. So when Webb observes a galaxy that appears surprisingly massive or luminous at a very early cosmic epoch, astronomers have to ask, did galaxies grow faster than expected? Did the stars form more efficiently? Are we overestimating the galaxy's mass? Could active black holes be contributing significant amounts of light? Or are there aspects of early galaxy formation that our models have not fully captured? These questions are much more important than the sensational claim that Webb has broken the Big Bang. It has not. The Big Bang model is supported by many independent observations, including cosmic expansion, the cosmic microwave background, and the abundance of light elements. What Webb is testing is something more specific. How quickly and efficiently did the first galaxies and stars form within that expanding universe? And the answers are still being refined. One of the most important tools for answering these questions is spectroscopy. When Webb observes the spectrum of a galaxy, the light is separated into different wavelengths. Atoms and molecules interact with light in characteristic ways. They can absorb or emit radiation at particular wavelengths. These features act like fingerprints. By analyzing them, astronomers can determine the presence of certain elements and molecules, estimate physical conditions, measure velocities, and determine redshifts with much greater confidence. This is particularly important for extremely distant galaxies. An object can appear very red simply because of its redshift, but its detailed spectrum provides far more information about its true nature. Webb's instruments can therefore move astronomy beyond the question of what does this object look like, toward the much more powerful question, what is this object physically doing? The same principle applies to exoplanets. When a planet passes in front of its star from our point of view, the planet can block a tiny fraction of the star's light. But some of that light passes through the planet's atmosphere. Different molecules absorb different wavelengths. By analyzing the resulting spectrum, astronomers can search for molecular signatures. This technique is known as transmission spectroscopy. It is an extraordinary concept. A planet may be hundreds or thousands of light years away. We cannot travel there. We cannot photograph its surface directly. Yet the atmosphere can leave a tiny chemical imprint in the light of its star. And Webb can attempt to detect that imprint. But detecting a molecule does not automatically mean detecting life. This distinction is crucial. A molecule such as methane, carbon dioxide, water vapor, or other compounds can be produced through many different physical and chemical processes. Even a combination of molecules that appears interesting must be interpreted in the context of a planet's temperature, atmosphere, star, geology, and chemistry. Webb can provide clues. It cannot, by itself, declare that an alien world contains life. The same caution applies to some of the telescope's most famous observations. When a distant galaxy appears unexpectedly bright, that does not automatically mean our fundamental understanding of cosmology has failed. There are many factors involved. The galaxy's stellar population may be unusual. Its star formation rate may be extremely high. An active supermassive black hole may contribute to its brightness. Dust can alter what we see. Gravitational lensing can magnify distant objects. And early estimates can change as better data become available. This is why scientists do not interpret Webb's images in isolation. They compare them with theoretical models and observations from other telescopes. They examine statistical populations rather than relying only on one spectacular object. And they look for patterns. If hundreds or thousands of early galaxies consistently behave differently from predictions, that would be much more significant than a handful of unusual examples. This is one of the great strengths of Webb. It is not simply searching for the strangest object in the universe. It is building a much larger sample of cosmic history. And as those samples grow, astronomers can begin to ask statistical questions. How common were massive galaxies during the first billion years? How rapidly did star formation increase? When did the first generations of stars appear? How quickly did galaxies become chemically enriched? How did supermassive black holes grow? And how did all these processes interact? These questions are connected. A galaxy is not an isolated collection of stars. It is part of a larger gravitational ecosystem. Gas flows into galaxies. Stars form. Massive stars explode. Black holes consume matter. Energy and radiation influence surrounding gas. Galaxies merge. Dark matter provides much of the gravitational framework. The result is an evolving cosmic system. And Webb is allowing scientists to observe more stages of that evolution than ever before. One of the most remarkable aspects of these observations is the presence of extremely distant galaxies with active star formation. When stars form rapidly, enormous amounts of ultraviolet radiation can be produced. That radiation interacts with surrounding gas. It can influence the chemistry and temperature of the galaxy. And when massive stars die, they can release heavy elements and energy into the surrounding environment. Over cosmic time, these processes help transform a relatively simple early universe into the chemically rich universe we see today. There is also another major mystery. Supermassive black holes appear to exist surprisingly early in cosmic history. Some ancient galaxies contain evidence of powerful active galactic nuclei, powered by matter falling toward massive black holes. But how did some black holes become so massive so quickly? A black hole can grow by accreting matter. It can also grow through mergers with other black holes. But there are limits to how rapidly this growth can occur under ordinary conditions. If very massive black holes existed only a few 100 million years after the Big Bang, their origins could provide important clues about the earliest stages of structure formation. Webb is helping astronomers find and study these early active galaxies. Again, the observations do not automatically overturn established physics. Instead, they force scientists to investigate which growth mechanisms could have operated in the young universe. Perhaps some early black holes began from unusually massive stellar remnants. Perhaps dense gas clouds collapsed directly into massive black hole seeds. Perhaps early accretion was more efficient than simple models assumed. Or perhaps multiple mechanisms contributed. The evidence is still being assembled. And this is what makes Webb so scientifically valuable. It does not simply answer questions. It creates better questions. Every distant galaxy is a fossil record. Every spectrum is a clue. Every unexpected structure is a test. And every observation helps refine the story of how the universe evolved from a hot, relatively simple early state into the enormous cosmic web we see today. But there is a deeper question beneath all of this. If Webb can see galaxies from only a few 100 million years after the Big Bang, how close can it actually get to the beginning? Can it see the first stars? Can it detect the first galaxies? Can it identify the moment when the universe's first sources of light transformed the darkness? And if the telescope finds objects that appear too mature for their age, will the explanation come from better understanding galaxy formation? Or will it reveal something more fundamental about the physics of the early universe? Those questions remain open. And the observations made so far have shown us that the early cosmos was not a simple, empty place waiting for galaxies to slowly appear. It was dynamic, violent, rapidly evolving, and perhaps far more efficient at building cosmic structures than we once imagined. To understand just how much Webb has changed our picture of the universe, we now have to look at what the telescope has actually established so far, and which of its most extraordinary discoveries remain genuine mysteries. After years of observations, one thing has become clear: the James Webb Space Telescope has not simply given humanity better pictures of the universe. It has given us a more detailed history of how the universe became what it is today. And perhaps the most important discovery is that the early cosmos was already far more active and complex than a simple picture of slowly forming galaxies might suggest. Webb has observed galaxies from remarkably early periods in cosmic history. Some of them existed only a few 100 million years after the Big Bang. Their light has been traveling toward us for more than 13 billion years. When we see them, we are not seeing distant galaxies as they look today. We are seeing ancient versions of them. In some cases, we are observing galaxies from an era when the first generations of stars were still transforming the universe around them. And this has changed the questions astronomers are asking. We are no longer simply asking whether galaxies existed that early. We are asking how they managed to form, how quickly they grew, how efficiently they produced stars, and how their black holes became so massive. Webb has also helped reveal that some of the earliest galaxies were surprisingly diverse. Some were compact. Some were actively forming stars. Some contained evidence of powerful central black holes. Others showed signs of complex structures developing remarkably early. But here we must return to an important scientific principle. An unusual observation is not automatically a contradiction of the standard model. As Webb has collected more data, some of the initial surprises have become less mysterious. Improved distance measurements, better models of stellar populations, gravitational lensing calculations, and a more detailed understanding of how galaxies produce light can significantly change how an object is interpreted. Some galaxies that initially appeared impossibly massive were later found to have properties that made them less extreme than the first estimates suggested. This is not a failure of science. It is science working exactly as it should. A first observation creates a hypothesis. More observations test it. And when the evidence changes, the interpretation changes. But not every mystery has disappeared. Some questions remain genuinely difficult. One of them concerns the rapid appearance of massive galaxies. The universe was young. There had not been billions of years for galaxies to merge and evolve. Yet Webb has found galaxies that require us to understand how quickly matter could collapse, form stars, and build increasingly complex structures. The answer may involve processes that were more efficient in the early universe than they are today. Young galaxies may have experienced intense bursts of star formation. Gas could have been converted into stars at extraordinary rates. Dark matter halos may have assembled rapidly in certain environments. And some galaxies may have been unusually bright because of active black holes. These possibilities are being investigated. But the deeper Webb looks, the more important another question becomes. What were the first stars actually like? The earliest stars are often called population 3 stars. They would have formed from material containing almost no elements heavier than hydrogen and helium. Because those stars would have been made from chemically primitive material, they could have differed significantly from most stars we see today. Some theoretical models predict that the first stars could have been extremely massive. Their lives would have been short. But when they died, they could have released the first heavy elements into the surrounding universe. Those elements then became the raw material for later generations of stars, planets, and eventually complex chemistry. Webb is searching for indirect evidence of these first stellar populations. So far, detecting an unmistakable population 3 star remains an enormous challenge. We have strong theoretical reasons to expect that such stars existed. But direct identification remains elusive. And this is where Webb's mission becomes particularly profound. It is not simply searching for the oldest galaxy. It is searching for the first stages of cosmic transformation. The moment when darkness began giving way to starlight. The moment when the first stars began enriching the universe with heavier elements. The moment when the first galaxies began building the structures that would eventually lead to galaxies like our own. And then there is another mystery. The early universe eventually underwent a dramatic transition known as cosmic reionization. The universe was once filled largely with neutral hydrogen. The first stars and galaxies produced enormous amounts of energetic radiation. That radiation gradually ionized the surrounding hydrogen. Over time, vast regions of the universe became ionized. The exact details of how this happened remain an active area of research. Which galaxies contributed most? How quickly did reionization occur? How were ionizing photons able to escape from early galaxies? And how did the process unfold across the enormous cosmic web? Webb is helping answer these questions by observing early galaxies and measuring their properties. But perhaps the most exciting part of Webb's mission extends beyond the distant universe. it is also looking much closer to home. Within our own galaxy and nearby galaxies, Webb can observe stellar nurseries hidden behind clouds of dust. Infrared light is particularly useful because it can penetrate regions that visible light struggles to reveal. Inside these clouds, stars are being born. Some are surrounded by disks of gas and dust. Those disks may eventually produce planets. By studying them, Webb can investigate how planetary systems begin. And that connects the telescope's observations of the early universe with one of the most personal questions in astronomy. How did worlds like our own become possible? The answer is not found in one observation. It is a chain of cosmic history. The Big Bang produced mostly hydrogen and helium. Stars formed. Stars manufactured heavier elements. Those elements were dispersed into space. Later generations of stars and planetary systems formed from enriched material. Around some of those stars, planets emerged. On at least one of them, chemistry eventually became biology. Webb is observing different chapters of this story simultaneously. It can look billions of years into the past while also studying planetary systems forming today. That is one of the reasons the telescope is so extraordinary. It connects the origin of galaxies with the origin of worlds. And then there are the exoplanets. Webb has begun analyzing the atmospheres of worlds outside the solar system with unprecedented sensitivity. Some of these planets are nothing like Earth. They may orbit their stars extremely closely. They can have temperatures thousands of degrees above the conditions on our planet. Their atmospheres can contain exotic chemistry driven by intense radiation. Others may be smaller and cooler, making atmospheric measurements much more difficult. The ultimate goal is not simply to find an Earth-like planet. It is to understand how planetary atmospheres work. What molecules are present? How did they form? How do they change over time? And could some atmospheric combinations eventually provide evidence of biological activity? That final question remains extraordinarily difficult. Webb can detect atmospheric molecules. But no single molecule is a guaranteed signature of life. A substance associated with biology on Earth can sometimes be produced through non-biological processes elsewhere. So even a potentially intriguing atmospheric detection would need to be tested against alternative explanations. This is why scientists are cautious. The discovery of life beyond Earth would be one of the greatest events in human history. But extraordinary claims require extraordinary evidence. And Webb is designed to collect that evidence carefully. As of today, the telescope has already transformed our understanding of distant galaxies, star formation, planetary atmospheres, black holes, and the early universe. But it has not answered every mystery. In some ways, it has multiplied them. We still do not know exactly how the first galaxies grew so rapidly. We still do not have a direct detection of the first population 3 stars. We still do not know precisely how the earliest supermassive black holes became so massive. We still do not fully understand dark matter or dark energy. And we still do not know whether the atmospheric chemistry of any distant exoplanet will eventually provide compelling evidence for life beyond Earth. Yet perhaps that is the most appropriate ending for a telescope like James Webb. It was never built to give humanity a final answer about the universe. It was built to see farther, to see earlier, to see through cosmic dust, to separate ancient light into its chemical fingerprints, to test our theories against reality. And every time it does that, it reminds us of something extraordinary. The universe is not a finished story. It is still revealing itself. The faint infrared light collected by Webb may have begun its journey when the first galaxies were only beginning to form. Some of that light traveled for more than 13 billion years. It crossed an expanding universe. It passed through regions of space that had not yet become what they are today. And eventually, after all that time, a few photons reached a mirror orbiting far from Earth. They were captured, converted into data, analyzed by scientists. and transformed into knowledge. That is what makes James Webb so extraordinary. When we look at one of its images, we are not simply looking at a beautiful picture. We are looking at evidence. Evidence of stars that existed before our sun. Evidence of galaxies that formed when the universe was still young. Evidence of planets orbiting distant suns. Evidence of a cosmos constantly changing across unimaginable spans of time. And perhaps, hidden somewhere within all that ancient light, are answers to questions we have not yet learned how to ask. The James Webb Space Telescope has shown us an ancient universe. But it has also shown us something about ourselves. That from one small planet, around one ordinary star, we can build a machine capable of collecting light that has crossed the cosmos for billions of years. We can decode that light. We can reconstruct the history it carries. And we can look into an almost unimaginable past and recognize our own place within it. There is still so much we do not know. But perhaps that is precisely why the journey continues. Because every distant galaxy is another piece of the cosmic puzzle. Every unexpected observation is another challenge to our assumptions. And every new discovery brings us one step closer to understanding how the universe became the place we see today. James Webb has already changed our view of the cosmos. But its greatest discovery may not yet have happened. Somewhere in the darkness, billions of light years away, ancient light is still traveling toward us. And when those photons finally arrive, they may reveal something about the universe that no human being has ever seen before.